Hi, my name is Elrid, and today I will be sharing my findings in Lab 4 Circuits. This lab aims to demonstrate how circuits work by measuring potential difference within the circuit and analyzing the relationship between resistors in the form of light bulbs and capacitors to determine an RC value. I accomplish this by modeling circuits in Colorado FET's circuit construction kit and using their built-in voltmeter, ammeter, and stopwatch tools to take measurements. And from this, I found my RC value to be 5.9 seconds. Some guiding principles include the node rule, which says the sum of currents going into a node equals the sum of currents going out, and the loop rule, which says the sum of the potential differences within a loop in a circuit equals 0, and Ohm's law, which describes the relationship between resistance, current, and voltage. Additionally, to understand the relationship between resistors and capacitors, we know that the discharge of a capacitor follows exponential decay, so taking the natural log of this relationship gives us a plot that can help us determine our RC value, which is the time at which the voltage difference has dropped to 1 over E of its original value. Looking at my initial setup, I have two 1.5 volt batteries in series to give a total EMF of 3 volts connected to two resistors, one at 47 ohms and one at 100 ohms, and two ammeters, whose readings are independent of how they are hooked up. When we break the circuit and measure the potential difference, we see that it is the same as the EMF. And from measuring the potential difference on the closed circuit at different points, we obtain these voltages, with the current from the ammeter reading at 0.02 amps. Plotting the voltages as we traverse the circuit, we see that the net voltage across the loop is 0, satisfying the loop rule, and from this, we can confirm the resistance of the resistors and the lack of resistance in the ammeter and wires using Ohm's law. Finally, adding an ammeter in parallel with the 100 ohm resistor increases the current of the circuit because the electrons flow freely through the ammeter route since there is no resistance there. Looking at my RC circuit, the 10 ohm bulb was initially bright, but as the capacitors charged, it dimmed. Removing the battery and completing the circuit let the capacitor discharge with the same bulb effect and time as charging. This result was consistent with the 20 ohm bulb with double the times. Using a 30 ohm bulb, I recharged the capacitor and set a voltmeter across the capacitor and timed the discharge and recorded voltages. Using the natural log equation from the introduction, I plotted ln delta V over delta V naught versus time to get a line of best fit, whose slope is the inverse of the RC value, which I determined to be about 5.9 seconds. To end, if I used a real ammeter, since actual ammeters have some resistance compared to the 0 ohm resistance of my ideal ammeters, they would read lower current than what I observed in the simulation. If we use real batteries and capacitors, we would be adding additional factors into this lab, such as the internal resistance of the battery and capacitor, making the charging of the capacitor slower. Thank you for watching.